Bonjour. Welcome back to more statistics with Ms. Jacobs. All right. So I talked about this with several of you today in class, but for those of you who we didn't have a chance to check in, problem 2 here on the first page of the Unit 2 review is really about averages, just different ways to find averages. So last year, Math 1 students took concept quizzes, 11. On the initial systems of equations concept quiz, first period had 24 students and averaged a 3.5. 24 students and averaged a 3.5. Second period had 21 students and averaged 2.6. And third period had 31 students and averaged a 2.8. What was the overall average for all of the students combined? So you have two ways you could do this. They're basically accomplishing the same thing. It's just 6 of one, half a dozen of the other. The way I think about this is there's 24 students who got 3.5. That's probably not what actually happened, but the easiest way to get an average of 3.5 is if everyone got a 3.5. Then for second period, there were 21 students. They averaged a 2.6. Third period had 31 students and averaged a 2.8. And so right now, what this is essentially accomplishing is instead of writing out 3.5 24 times, I'm just saying, okay, that happens 24 times. So it's just a very basic finding the average. You add up all the numbers. We just have a lot of repeating numbers. So we're using multiplication to make our writing simpler. Then we're going to divide by the number. So in this case, the number of students is what we want to divide by, the average per student. So we can just add up our class sizes, 24, 21, and 31. And when we do this, we get 24 times 3.5, 1 times 2.6, 31 times 2.8, divided by 24 plus 21 plus 31. If you're going to do this in your calculator all in one fell swoop, make sure you put parentheses around your whole numerator and parentheses around your whole denominator. And that ends up giving us 2.966. So if you happen to just average the scores, you probably still got something very, very close to this because the class sizes are not that crazy different in size. And the one with the highest score wasn't that many. So the other way you can do this, and especially if you have more than 3, 1, 2, 3, is to put these in your lists. And so you're going to do L1 with the scores, 3.5, 2.6, and 2.8. And then L2 with the frequencies, 24, 21, 31. Then you'll do one variable statistics, just stat calc one variable statistics, and make sure you use list 2 as your frequency list. Great. So for question B, a student has taken 3 exams so far for a class and scored an average of 88. Okay, so 3 exams at 88. There are 5 more tests this semester. Okay, 5 more. What must the student's average be on those 5 tests in order for her overall test average to be a 92? So again, anytime we're dealing with averages, think about what makes an average. An average is just the sum. Oh, that's a crazy sigma over the number. And that's going to give you your average or your X bar, depending on your situation. So let's think about our sum. 3 of the tests are going to be 88 points. Again, easiest way to get an average of 88 is if they're all 88. So I'm going to say 3 times 88. And then there's 5 more tests, but we don't know what she's getting on these tests. So that we're going to use an X for, right? When we don't know, we'll use a variable. divided by, well, all together, there's going to be 3 tests and 5 tests. So that's going to make 8 tests. And when we do all that, we want to get 92. Now it's just algebra. We're going to multiply both sides by 8, clear that denominator. And 92 times 8 is 736. So 3 times 88 is 264. So 264 plus 5x is equal to 736. Subtract the 264 from both sides. 36 minus, type your numbers correctly. And we get 5x equals 472. Divide both sides by the coefficient on x. And we get that she needs to average 94.4 on her next 5 tests. So again, when you're finding an average, just always think about sum over number. Very frequently, you got to be changing something in that sum. Okay. In this question, I goofed last year and then forgot to leave myself a note to fix it for this year. So there's actually 2 right answers here. Following segmented bar chart shows the number of flights. Okay, so let's keep track that it's the number of flights that were either on time or delayed at 3 different airports on one day. We've got that. Here are the airports. Here's the number of flights. I'm going to make note that this is number again. The reason I'm emphasizing that is it's important that it's number and not percent, right? A relative frequency, anything like that. That's going to change how we approach it. So which of the following statements is not supported by the bar chart? Anytime you see the word not, I want you to underline it, box it, do something. Even if it's already bolded or capitalized, for some reason, it's just a real easy word for your brain to forget. So let's start with A. We're just going to take these one at a time. Airport T had more delayed flights. Okay, so the delayed flights are this gray. So that's here, delayed flights. Then the total number of flights at the other 2 airports combined. So Airport S, we can see that the total number of flights looks to be like right at 200. And then that takes up this whole chunk. So Airport S basically fits into this bit. Airport R is certainly more than 100, and it's on its way to 200. So right here, that looks like maybe it's right around 100. Airport R is going to exceed, and that's a little tall, but it's going to exceed this by a little bit. I think. Yeah. All right. So Airport T had more delayed flights than the total number of flights at the other 2 airports combined. Looking at it super closely, it's a pretty close call. I would say no, but don't expect things to be this close. This is not from College Board. This is a little bit too close and not labeled clearly enough to tell. So this is one of our not supported, I would say. B, Airport T had more on-time flights than did Airport R. Well, yeah, the number is definitely higher for Airport T. The number of on-time flights is about 200. The number of on-time flights here is about 100. So that we can definitely cross out. It's not supported. C, the percentage of on-time flights was higher at Airport T than at Airport R. So the percentage of on-time flights at Airport T looks to be about 200 out of 500. So 200 out of 500 would be about 40%. This is really unambiguous. The percent of on-time flights at Airport R, almost all of them are on time. So it's certainly more than half. I don't even need to do the calculation there. I know that the percentage here is higher at R. So this is not supported for sure. So this one is maybe it's not as wrong as I thought. D, the percentage of on-time flights was higher at airport R than at airport S. Again, we can see that this is about half or less, and this is more than half. So when we get it to a percentage, this is totally true. The total number of flights at airport S was about equal to the number of on-time flights at airport T. That totally. On-time flights come to here for airport T, total number of flights at airport S hit the exact same mark, right around 200. So that is supported. It is not what we want to choose. So I think this is the most clearly not supported. And then this one, if I were writing this question, I would include more structure in the way the graph was built so that you could really clearly see, oh, this is exactly the same versus it's a little close. All right. This FRQ. Again, lots of people asked me questions about this today, which is great. So let's go through it. A student measured the heights and the arm spans, rounded to the nearest inch, of each person in a random sample of 12 seniors at a high school. A scatter plot of arm span versus height for 12 seniors is shown. So here's our scatter plot. Part A, based on the scatter plot, describe the relationship. Underline scatter plot and describe the relationship between arm span and height for the sample of 12 seniors. When we are describing scatter plots and describing the relationship between two quantitative variables, we need direction, form, and strength. So the direction here is positive. So your direction is going to be positive or negative. The form, it looks roughly linear. And remember, for our purposes, we're going to say linear or nonlinear. So we're going to say linear here. And strength, I would say that's like moderately strong. So to actually answer this question in context, the context just becomes so key. There appears to be a moderately strong positive linear relationship between height and arm span. It seems tedious. We just were told it's about height and arm span. Still include it. Context is just such an easy place to pick up points or lose points if you leave it out. Okay, so that's part A. Now, let X represent height in inches and Y represent arm span in inches. Two scatter plots of the same data are shown below. So these are the same scatter plots as up here. Now we've got some lines in them. Graph 1 shows the data with the least squares regression line with this equation. So I'm going to just say that this is LSRL. And graph 2 shows the data with the line y equals x. Y equals x. Great. So that's just giving us some information. Underline that. The criteria described in the table below can be used to classify people into one of three body shape categories: square, tall rectangle, or short rectangle. This is made up for this test. This is not like a stats thing that you should know. This is, we're going to give you information and see if you can read it and process it and use the information on the graphs to answer questions. So don't worry if you were like, I have no idea what they're talking about. So first part, for which graph, 1 or 2, is the line helpful in classifying a student's body shape as square, tall rectangle, or short rectangle? So square is particularly helpful here. Arm span is equal to height. With this line, this is the line of best fit, but it's pretty difficult to see where arm span is exactly equal to height. This line is our line y equals x. So this is showing us the place where the height and the arm span are equal. So graph 2 is more helpful. Because the line y equals x will show where height and arm span are equal, which would be square, and then the dots above are short rectangles because the arm span is greater than the height, right? If we looked at this, arm span is 64 right here, but the height is only like 61. Short rectangles. And the dots below are tall rectangles. Okay. So a lot of folks picked the right graph. The explanations have to be pretty strong. We want to be as specific as possible. That BSing is across the board. Now, part 2. Complete the table of classifications for the 12 seniors. This says frequency, not relative frequency. That means it's just going to be a number in these boxes. If it wanted relative frequency, then we would do the number relative to the total. So keep an eye out for that word relative or its absence. All right, so for square, arm span is equal to height. If I look, I've got 1, 2, 3 right on the line. So there are 3 square seniors. Then, so right here, the arm span was longer than the height, greater than the height. So there are 1, 2, 3, 4, 5 instances of that, and that's a short rectangle. And then 1, 2, 3, 4. The ones below would be tall rectangles. You could also say, well, this makes 8, and to get to 12 seniors, we'd have 4 left. Okay. Using the best model for prediction, calculate the predicted arm span for a senior with a height of 61 inches. So this graph was the best model for classification along this kind of silly thing. This is the best model for prediction. This is the line of best fit. That's what we want to use for our prediction, not our y equals x. The equation's down here again, so I'm going to use that one. So we'll say y hat is equal to 11.74 plus 0.8247 times our input of 61 inches. And we just calculate that. 11.74 plus 0.8247 times 61. And we get the predicted height is about 62.05 inches. Doesn't ask you to explain. Definitely show your work. Always set up what you're going to calculate in writing. But that's it. Part D, would it be reasonable to use the fitted regression equation, so this line of best fit, to predict the arm span of a student whose height is 87 inches? Explain. Looking at our graphs, this goes from 60 to 72. 87 is way out here. It's 15 past our last X value. And this data set only even ranges from 60 to 72, which is 12. So again, this could kind of go one way, could kind of go the other. It depends on the strength of your explanation. I'm going to say because the height of 87 is outside the range of X values, used to create the model, it would be an extrapolation. So again, that word extrapolation is when the input value is outside the range of inputs used to create the model, and therefore potentially unreliable. Again, 87's kind of close. Like, that's a super tall person, but it's within the range. It's not 187. It's not 4. So it's kind of a judgment call. It is definitely an extrapolation, and you probably don't want to use this model just because of that. But realistically, this model might not be that terrible. Okay. From the fitted regression equation, interpret the meaning of the slope in context. This is where those sentence stems come in. So the slope was 0.8247. And so the way you'll write that is, for every additional, and in this case, our x variable is height. So inch of height. The arm span is predicted to increase approximately 0.8247 inches on average. So this might be a bit of overkill, but you definitely need at least one of these, right? Predicted, approximately, on average. You have to indicate that our regression equation is a prediction, that it is not a guarantee. For this guy, for F, from the fitted regression equation, interpret the meaning of the y-intercept in context. Is this meaningful? So this would be for someone with a height of 0 inches, we predict an arm span of 11.74 inches. Not meaningful. No one is 0 inches tall, not even when you're born. And certainly if you are 0 inches tall, why was your arm span almost a foot? Right? It's nonsensical. Every line has a y-intercept, so every regression line has a y-intercept. It does not always make sense in context. Okay. Moving right along. This one is very similar to the first problem on the first page of the Unit 1 review. So, manufacturer claims that lifespans for their printers in months can be described by a normal model. Okay, so check, we're going to use normal stuff. This is our mean. This is our standard deviation. Hey, what's the third quartile? Well, 3/4 is equal to 0.75. Since we have a proportion or a percent or a probability, again, those P words, we're going to say inverse norm with an area of 0.75, a mean of 60, and a standard deviation of 3. And it's just going to pop out our answer. So second vars, inverse norm, area is 0.75, mean is 60, standard deviation is 3. If you have the option, set the tail to left because we want the third quartile, so the 75th percentile. And that gives us 62.02. So that would be months in context. Next, what's the z-score for a printer with a lifespan of 64 months? What does this mean? Okay, z-scores are always value minus the mean over the standard deviation. So our value here, our point of interest is 64. Our mean is 60. And our standard deviation is 3. So this gives us 4/3. This might be a good place to use mixed numbers. Generally, I don't like mixed numbers. In terms of what does this mean? This printer's lifespan is 1 1/3 standard deviations above the mean. So because it's positive, it's above the mean. And the z-score always tells us how many standard deviations we are from the mean. That is what a z-score is. All right, what percent of the printers are expected to fail before 56 months? I'm just going to draw a little curve here. So here's 60. And 56 would be maybe about here. And the area that we're interested in is failing before. So before we get to 56, that's all this stuff to the left. So we want to find that area. So we're looking for a percent. What percent? This is your clue for normal CDF. So we'll say normal CDF. Our lower is, again, just negative infinity. You can do negative 99999. You can do negative 1 times 10 to the 99th. Make sure when you're putting this in your calculator, you're using the negative sign right under the 3, not the subtraction symbol. You will get a syntax error if you use the subtraction symbol. Our upper bound is going to be our point of interest, 56. Our mean is 60. Our standard deviation is 3. And again, this is just going to pop out that percent. So 56, mean is 60, standard deviation is 3, boom. So that's about 0.091. So 9.1%, horrible. 9.1% of the printers are expected to fail before 56 months. Cool. The last part of this problem, this was probably the trickiest part. The printer manufacturer makes some changes, and now 10% of the printers last more than 65 months. Assuming the mean lifespan will stay the same, what is the new standard deviation? All right, big red flag here. New standard deviation. That means whatever we do, we're going to have to work in standardized scores. So the mean is going to be 0 and the standard deviation is going to be 1. If you don't know either the mean or the standard deviation, and that's what you're trying to find, you are probably going to be using a z-score. So again, z equals value minus mean over standard deviation. So you're probably going to be using a z-score, and you're probably going to be using mean as 0, standard deviation as 1. The other thing is 10% of the printers last more than 65 months. So more than 65, that means we're talking, there's the mean, here's 65. We're talking about the stuff over here. That's 10% right there. The inverse norm function, and we're looking for a z-score, we have a percent. The inverse norm function gives you what's to the left by default. Some of the newer calculators, you can set it to be centered or to the right, but generally speaking, it gives you what's to the left. So if 10% is to the right, we can just do 1 minus 10% to get that same position from going to the left. So this is going to leave us with 0.9. So again, because we have a percent, we're going to use inverse norm. And we're going to put in the area of 0.9. That's our area. Our mean is going to be 0. And our standard deviation is going to be 1. When we do that, we get a z-score of 1.28. So it's positive, which makes sense because this is above average. Now we can use the z-score formula and algebra to calculate what that standard deviation would have to be. So we'll say 1.28 is equal to our value, 65, minus the mean, which is staying the same, 60 from the previous bits of the question, all over our standard deviation. We don't know what that is, so we'll use a variable. I'm going to multiply both sides by s. And I really strongly recommend that you just write out your algebra. I saw a lot of people solve this. So you did all the challenging stuff right, all the new stats stuff right. And it was just the algebra that got you turned around. So this is going to cancel out our s's. We're left with 1.28 s on this side. And 65 minus 60 is positive 5. We'll divide by the coefficient on s. And we get the standard deviation, 5 divided by 1.28 is 3.91. Now, you could do 5 divided by the last thing your calculator put in rather than rounding it. If you're going to round, go several decimal places out. The AP Stats test isn't super picky about rounding, but it is possible to round too aggressively and too early. All right, so there's our new standard deviation. Again, we have a percent, so we used inverse norm. Up here, we wanted a percent, so we used normal CDF. Cool. Finding the 5-number summary and creating a box plot, we did one of those in the previous one. So you can check the answer key. I'm not going to go through this again. These, again, were repeat questions. All right, so question 8, this is a newer one. This is a Unit 2 one. Both the x and y variables are standardized, and an equation for the least squares regression line is calculated. This is what's important. The x and y variables are standardized. The slope of the least square regression line is negative 0.72. What can we conclude? So if the variables are both standardized, then if x and y standardized, so basically turned into a bunch of z-scores, then and only then the slope of the least squares regression line is equal to the correlation. So that's what we're looking for here. We're not talking about intercepts. The correlation is also negative 0.72. It only happens when the variables are standardized. In all other cases, the slope and the correlation are not the same thing. Question 9 again. Repeat from Unit 1. Did I have 2 question 9s? I do. Cool. So this question 9, this is a newer one. Consider this linear regression output for how long it took a 5-gallon bucket to drain based on the volume of water inside. Based on, so that's going to be our x. Looking at this regression output right now, don't use anything to the right of the first set of numbers. None of this is what you want right now. This S you also don't want right now. This might come up. And so leave that, but it's not part of your regression equation. So in this, you're going to have your constant. That is your y-intercept. And whatever with your variable, or if there's an x there, that is your slope. So when they say, what is the least squares regression equation? We say y hat is equal to our y-intercept plus 9.952 x. If you're going to use variables, define your variables. So y hat equals how long it took, predicted drain time. And x equals volume of water. You could also just put the words in parentheses. All right. Using your equation, what is the predicted drain time for a bucket with 1.75 gallons of water in it? Great. We're just going to plug 1.75 in. I'm going to be a little lazy there and duplicate it. And instead of the x, I'm just going to put in 1.75. So this would be 20.133 plus 9.952 times 1.75. And our predicted drain time is 37.55. I didn't specify a unit of time. It's probably seconds, but I didn't specify. All right. C, the actual drain time for a bucket with 1.75 gallons of water is 40 seconds. What is the residual for this data point? So again, the residual is the distance or difference between your actual value and the predicted value. So actual minus predicted equals the residual. And so in this case, actual was 40, predicted was 37.55. And so the residual is 2.451. Okay. So this is positive, which means that the prediction was a bit of an underestimate for how long it would take to drain. Here, a bucket with a volume of 3 gallons has a drain time with a residual of 1.011. What is the actual drain time? Again, this is just algebra. So the actual is what we're looking for. The predicted, we're going to have to plug 3 gallons into this equation. So we can just do that right here. 20.133 plus 9.952 times 3 equals, and then we know the residual is 1.011. So we'll plug this into a calculator. So our predicted now is 49.989. And we're just going to add that to both sides. .011. And we get that the actual drain time was 51 units of time. So again, it's all about setting up the equation and plugging in the numbers you know and finding the ones you don't. Okay. A linear regression is performed for another set of bucket data, and the correlation is 0.8304. Which of the following is correct? All right. If you are given a correlation, go ahead and square it. It'll take you almost no time. And then you'll have the value for if you actually want to talk about R squared. So R squared here is 0.6896. Okay. So 83.04% of the water drains from the bucket in the predicted time. That is not what R squared talks about, and it's not what R talks about. The model accounts for 83.04% of the variation in times. So that's getting closer. But again, this is pretty much what R squared is, not what R is. So we can't say it about R, but we can say it about R squared. So the model accounts for 68.96% of the variation in times. Yeah. So that's going to be our answer. As the volume of water increases, the time to drain decreases. That's not correct because the correlation would be negative if we have an inverse relationship. our correlation would be negative. We'd have a negative slope. So that's just out for a lot of reasons. Okay, almost there. A student analyzing some data created a linear model with r squared equals 82% and having the residuals plot seen here. What should he conclude? Looking at this residuals plot, I see a bit of a curvature here. It's not crazy, but it's definitely, like, if I just look at it for a moment, I see a curve in there. So right away, I'm going to say the linear model is not appropriate. I'm going to find that linear model is not appropriate. This one says the linear model is appropriate. I'm just going to cross it out. Here, the linear model is appropriate. No, I disagree. Doesn't matter what it says after that. If I think there's a curve, that means a linear model is not appropriate. I can cross out anything that says otherwise. So A, because the residuals plot shows curvature, yeah, that's pretty much why. I'm going to circle that. Just check the other ones. Not appropriate because the residuals plot identifies an outlier. No, outliers are fine. You can have an outlier in a linear model. See, the linear model is not appropriate because the value of r squared is not high enough. This is actually quite a high r squared, but that doesn't determine whether a linear model is appropriate. The linear model is appropriate if there is no pattern in the residuals. There is a pattern here, so we're going with A. There's curvature. All right, two more. Identify the high leverage point in the graph. Okay, one of these things is not like the other. It's way out there. Explain why it has high leverage. So this point has high leverage because its x value is very far from the rest of the data's x values. Thus, it will make the correlation appear stronger. So we can imagine this is having a big impact. It's having high leverage on our graph. If we took this point out, these are way more all over the place, right? It would be way harder to even tell if that should be a positive or a negative slope, right? We could see a negative line in here, a positive line in here. So this point is really punching above its weight. All right. So lastly, identify the influential point in the graph. So on my version, it's a different color, which is nice. Explain why it's influential. So this point is influential because it has a very different y value than would fit with the rest of the data. And will have an outsize, so more than it should, impact on the slope and y-intercept. So you can kind of see if we took this point out, then our line would be much more like that. It would make our slope a little steeper. It would make our y-intercept a little bit lower. So this point is like basically taking this line and pulling it down. All right. I hope that was helpful. Please keep asking questions. Email me. Come see me after school tomorrow. I will be there. And good luck on your studying.